Hi, everyone, and welcome. I'm so excited to have you in cognitive psychology this semester. To get started, we're going to cover Chapter 1, which serves as an introduction to cognitive psychology and the types of topics we'll explore throughout the course. Every lecture, we're going to start out with our chapter goals, and our first goal today is to discuss some of the challenges and limitations in cognitive psychology. I like to start here because it helps us to understand the boundaries and limitations of our field, so we ensure that we don't overextend any of the theories or findings we're going to discuss later on. Next, we'll address a fundamental question. Why do we even study cognitive psychology in the first place? Why is this field so important? From there, we'll examine the current state of the field. Where does modern cognitive psychology stand today? Unsurprisingly, this means discussing artificial intelligence and how AI is shaping our understanding of human cognition. We'll also explore the standard three-pronged approach used to study cognition. While cognitive psychology is one prong, we will look at contemporary approaches, specifically neuroscience and computational modeling, to highlight just how interdisciplinary this field really is. Finally, we'll wrap up today by looking at how cognitive psychology applies in the real world, particularly through human factors and solving practical everyday problems. The first major topic we need to cover is the limitations and challenges in cognitive psychology. One primary limitation is that cognitive psychology largely deals with theories rather than absolute ground truths. While we have models supported by a substantial amount of empirical evidence, they still remain theories. We're not 100% certain that every model is complete or infallible. Because research is ongoing, our understanding continually evolves, and we have to become comfortable with ambiguity and competing hypotheses. Furthermore, published scientific literature is not always perfect. Researchers and textbook authors can make errors, which means we must remain critical and carefully evaluate study methodologies as we learn. One of the most significant issues in research methodology is publication bias, commonly known as the file drawer problem. Historically, academic journals have predominantly published studies with statistically significant results, traditionally where p is less than 0.05, meaning the null hypothesis was rejected. Studies that fail to find a statistically significant effect, where p is greater than 0.05, often get filed away in a drawer and remain unpublished. To understand why this is so problematic, imagine 100 studies conducted on a specific topic. 99 of those studies fail to find a significant effect. However, one singular study, perhaps purely due to just random chance, rejects the null hypothesis and gets published. If those 99 non-significant studies remain hidden away in a file drawer, the published literature creates a misleading impression that the effect is real when it may not be. To address this challenge, the scientific community is moving toward pre-registering studies. In pre-registration, researchers submit their hypothesis and methodology for peer review before data collection even begins. Participating journals commit to publishing the final results regardless of whether the analysis yields a statistically significant outcome. This directly mitigates the file drawer problem and moves the field forward. Maintaining scientific skepticism also means distinguishing legitimate cognitive research from pseudoscience, concepts that may sound appealing or fun, but lack empirical support. For example, consider graphology, which is the practice of analyzing handwriting to judge personality traits or psychological conditions. While graphology is popular in TV shows and true crime documentaries, it lacks rigorous scientific backing. The same is true for traditional dream analysis. Early theories suggested that dreams contain deep latent meaning about our psyche, but modern scientific evidence does not support the idea that specific dream content reliably reflects specific underlying psychological states. Perhaps the most famous example of pseudoscience in our field's history is phrenology. In the 19th century, phrenologists believed that bumps and grooves on the skull corresponded to underlying brain structures and traits like intelligence or personality. While phrenology itself turned out to be completely hogwash, historically, it prompted researchers to consider localization of function, the core principle that different regions of the brain serve distinct cognitive functions. Now that we've established those limitations, let us look at how we define and study cognition. What is cognition? Cognition is defined as the process of acquiring and processing information about the world in order to make behavioral decisions. If we unpack that definition, it highlights the exact progression we will take throughout this course. First, we acquire information. That is how we'll start this semester, examining the brain, sensory systems, and how we gather data from our environment. Next, we process that information through perception, memory, and language, interpreting and organizing the sensory data we take in. Finally, we use that processed information to make behavioral decisions, which includes higher level processes like reasoning, problem solving, and decision making. Cognition encompasses a vast array of mental abilities, including perception, attention, memory, language, and executive functioning. Cognitive psychology is an expansive field made up of many specialized subdivisions, such as human factors, human-computer interaction, cybersecurity, or cognitive ergonomics. To understand why we study cognition, it helps to distinguish between two main types of research: basic research and applied research. Basic research aims to understand fundamental processes and phenomena for the sake of knowledge itself, without immediate regard to practical applications. For example, basic research might investigate how cone photoreceptors function in the retina to understand the biological mechanisms behind red-green color deficiency. Applied research, on the other hand, focuses on developing direct solutions to real-world problems. For example, applied research helps design accessible user interfaces in video games, such as alternative color palette options in games like Destiny, so the colorblind players can easily distinguish between critical visual cues like green reapers and red invaders. This brings us to the state of the field today, which is heavily influenced by artificial intelligence. AI is a branch of computer science and engineering dedicated to building machines capable of performing tasks that typically require human intelligence. Historically, early conversational systems operated on rigid rule-based programming, such as if this, then that logic. While effective for simple, structured tasks, these early chatbots struggled to replicate flexible, adaptive human communication. Today, advanced generative AI systems such as ChatGPT, Gemini, and Copilot have made significant leaps in natural language understanding and object recognition. However, these systems still experience limitations such as hallucinating incorrect information, illustrating that current AI has not yet fully matched human cognitive ability. To study these complex cognitive systems effectively, modern science relies on an interdisciplinary, three-pronged framework: neuroscience, cognitive psychology, and computational modeling. Neuroscience investigates the physical brain itself, using modern, non-invasive neuroimaging tools like fMRI, EEG, and fNIRS. Researchers can observe brain activity in living human beings in real time. In animal research, invasive techniques like single-cell recording allow scientists to measure the precise electrical activity of individual neurons. Cognitive psychology uses experimental behavioral paradigms to infer how mental processes operate and how observable behavior connects to underlying cognitive structures. And computational modeling uses computer simulations and artificial neural networks to model cognitive functions. Because biological neural networks involve quadrillions of synaptic connections that exceed human processing power, machine learning models help researchers analyze and simulate complex cognitive architecture. Finally, let's discuss how cognitive psychology directly applies to real-world problems across everyday life. In medicine and neurorehabilitation, cognitive principles help us understand the ramifications of neurological damage, such as stroke in a temporal lobe, and show us how to leverage brain plasticity for cognitive recovery. In virtual reality and spatial design, cognitive research on depth perception and visual processing guides engineers in constructing realistic, immersive VR environments. In transportation safety, studying divided attention and cognitive load explains why texting while driving is so dangerous and helps us design safer driving technologies. When looking at short term and working memory, understanding our capacity limitations explains everyday phenomena, like why you forget items on a grocery list, and offers strategies to optimize memory retention. In the legal system, research on long term memory demonstrates that eyewitness testimony is reconstructive and fallible rather than a perfect camera recording, leading to critical policy reforms in courtrooms. When studying autobiographical memory, we explore how personal memories function, including the limitations and expected fallibilities of flashbulb memories from major life events. In computer science, cognitive theories of knowledge representation help AI developers address the common sense knowledge problem, such as teaching machines basic real world facts that humans take for granted. In language and human development, cognitive research highlights nonverbal communication strategies, such as teaching sign language to infants to facilitate communication before their verbal skills develop. In decision making and risk assessment, examining cognitive biases help us improve choices in financial markets, refine problem solving strategies, and build stronger cybersecurity awareness to prevent people from falling for phishing scams. To recall our main points from Chapter 1, we acknowledged key methodological limitations in research, including publication bias from the file drawer problem, theoretical ambiguity, and historical pseudoscience. We defined cognition as acquiring, processing, and acting upon environmental information. We distinguished between basic research for foundational knowledge and applied research for real-world solutions. We explored how cognitive science relies on a three-pronged approach combining neuroscience, cognitive psychology, and computational modeling. And finally, we saw how cognitive principles directly apply to technology, healthcare, safety, law, and human decision-making. Looking ahead, our next lecture will cover Chapter 2, How to Study Cognition. Thank you all so much for your time today, and I'll see you in the next lecture.